My name is John Eiler, and I'm the Robert P. Sharp Professor of Geology and Professor of Geochemistry at the California Institute of Technology. In my mind, there are two fundamental reasons for being interested in the study of the physiology and body temperatures of dinosaurs. One of them is a hard-minded scientific motivation. The dinosaurs were key components of the Mesozoic ecosystem, and we'd like to understand how they fit into that ecosystem. They were a sort of intermediate life form between the relatively metabolically simple, sluggish reptiles and fish that are ectothermic, that is, they derive their heat from the environment, and the more metabolically advanced, if you will, mammals and birds that are endothermic and generate their heat and control their body temperature through internal metabolic activity. A second general reason for being interested in dinosaurs is they're just intrinsically fascinating. They were titanic creatures that dominated the landscape. I think everyone would like to know what the Earth's historical dragons and monsters actually were like. How did they live? How did they behave? How did their bodies work? This has been one of the classic problems in paleobiology for over a century. Our measurement is the first that is a direct thermodynamically based determination that it yields a specific temperature with a relatively modest error bar. The hero of this story is Rob Eagle, who's a postdoctoral scholar at the California Institute of Technology and came here 2 years ago from Cambridge University, specifically to study the problem of dinosaur physiology and metabolism.
So for the project that we were interested in, which was reconstructing the physiology of extinct species, we were really interested in biologically precipitated minerals. And in this case, we were either focusing on teeth and also bone. In terms of our study, we were really interested in the enamel because it has very large crystals that don't have much organic matter interlaced in them. This is most resistant to chemical alteration over geological timescales.
The measurement we've done is based on a new type of isotope geochemistry that we refer to as clumped isotope geochemistry because it measures the extent to which rare naturally occurring isotopes stick to each other in the structures of minerals, molecules in air, and organic molecules. The first uses of this thermometer to study fossils focused on fossils that are made out of calcium carbonate minerals, like clam shells and corals. However, we discovered that you could also apply this technique to carbonate ion groups that are a trace constituent of the mineral apatite, which is what your bones and teeth are made of, and analyze them for their state of clumping or ordering, and therefore get their growth temperatures. This is the Laboratory for Stable Isotope Geochemistry, which has existed at Caltech since the early 1950s. The experiment that we do is a classic old-school analytical chemistry approach. The measurement was actually invented almost exactly the way we do it 60 years ago, except we've added one little tweak at the end that makes all the difference, that lets us turn a measurement that has been made for decades into a new sort of measurement. And here is the one thing that we're doing that's special, that makes this a new analysis. In addition to collecting the ion beams that correspond to isotopically normal carbon dioxide, we also collect the ion beams corresponding to molecules that have 2 rare isotopes or even 3 rare isotopes in them. And it is the comparison of all of these ion beams that allows us to determine the state of ordering or clumping of rare isotopes within the specimen. This is the first direct quantitative measurement of dinosaur body temperature.
So this suggests that sauropods were significantly warmer than modern cold-blooded organisms like crocodiles or alligators.
Actually, the problem in understanding sauropod physiology based on our results is not how they got so warm, but rather how they kept from being warmer. How did they dissipate their internal heat to keep themselves at a body temperature similar to modern mammals? So I was one of those kids that had a collection of many hundreds of little plastic dinosaurs, have them eat my Roman soldiers. I actually wrote my first dinosaur paper at the age of 6 called Dinosaurs Roar. It's been a lifelong interest. I feel very fortunate to be able to turn my scientific career back to that interest and try and solve some small part of it.
Remember some trips to the Natural History Museum in London, which were quite a formative experience for me. I studied and gained some training in evolutionary biology. I began to think of them less as sort of cool monsters
Well, that's where you left me behind. They're still cool monsters to me.